Good afternoon, everyone. My name is Ed McMahon, and I am the CEO of Epec Engineered Technologies. Thank you for joining us today for the next installment of our technical webinar series, which is High Reliability Keypad Design and Assembly. As many of you know, Epec has been a leading provider of printed circuit boards, flex and rigid flex printed circuit boards, custom battery packs, user interfaces, and cable assemblies for over 60 years. In June of this year, we made our 15th acquisition of a company called Suncoast Digital Technologies, which is located in Largo, Florida. A little background on Suncoast: they have been a leader for over 22 years in the design and manufacture of low-profile, high-reliability user interfaces, focusing primarily on the military, aerospace, medical, and industrial markets. Epec has always been focused on providing world-class technical and engineering support to our customers, and that is the major reason that we focused and spent a little over 2 years on acquiring Suncoast. The two gentlemen who ran this company for the 22 years and continue to work with us today have been in this business for well over 30 years. And as I get to know them more, it is clear they've forgotten more about user interfaces than all the rest of us know combined. So our presenter today, Paul Konupke, has experience on over 2,000 OEM designs. And these designs are for the most demanding application environments for customers such as Northrop Grumman, Lockheed Martin, L3, the U.S. Navy, and many, many others. Paul's focus today is to provide our listeners with real-world challenges that we face in high-reliability keyboard designs and how to overcome them. With so many years of experience and designs under his belt, Paul has seen firsthand how not preparing the design correctly for its operating environment can dramatically affect performance. And his goal today is to really help you understand what you're going to be coming up against. And after this, he is available to help design on any new designs that you may have. So without further ado, I'll turn this over to Paul, and he can go over all of the great technical and reference information that he's got for us today.
Thanks for the introduction, Ed. Again, welcome to this seminar covering high reliability keypad design and assembly. This webinar discusses the application of high reliability keypads and differences from typical keypads used for consumer grade or throwaway electronic applications. Topics covered are target markets, terms and definitions, basic core switch technology, factors that can help or harm long-term performance, and extending electrical and mechanical operating life. The target markets that we're interested in are those end applications requiring critical mission performance, long service life, or capital equipment applications where the cost of the keypad assembly is a tiny portion of the total equipment cost or expected service life. Another way of identifying our desired target markets is to look what is not included in those target markets. Keypad applications that are not considered our markets are those applications where the cost of the keypad is a very large portion of the total application cost or the application service life. This is very short as in throwaway electronics or keypad applications with very rapid obsolescence. In these throwaway product markets, holding down the total application cost usually outweighs long-term reliability, or the product will be obsolete due to rapidly changing technology. Therefore, long product life adds no real value. Taken together, Suncoast Digital Technologies keypad switch technology is a good fit to these target markets and should be a successful match. Let's look at some target markets. First is military electronics. We understand military electronics is a tough sell. However, once you're in a program and made it through first articles tests and approval, it's very difficult to be displaced by another vendor. The investment in time and energy for the customer to get to that first article stage is prohibitive to qualify another supplier. our return for the investment is rewarded by a virtual captive market and long program life. Satellite communications ground support equipment is another target market. Most people think of satellite communications as only the satellites orbiting around the Earth. However, the hidden part behind every satellite in orbit are the many ground installations that transmit data up to the satellite for retransmission and many other ground installations for receiving that data. It's critical that the satellite communications path is reliable because downtime is very expensive. The ground support equipment multiplexes many data channels together into a single data stream through the satellite, and at the other end, demultiplexes the data stream back to individual data channels. If the ground support equipment or the satellite goes offline, the total loss to the satellite carrier for the highly multiplexed data stream can be thousands of dollars per minute. Another target market is mobile communications. These applications include emergency communications for first responders, fire and safety personnel, military command and control, and communications equipment for soldiers on the ground or troop carriers, tanks, and combat vehicles. Medical electronics is another target market that includes operating room electronics as well as patient monitoring and medical diagnostic equipment. Electronic test equipment is a target market because of its high cost and very long service life. Most sophisticated RF and microwave test equipment used for testing state-of-the-art electronics and high-frequency circuits can cost anywhere from $10,000 to over $100,000 per instrument. Electronic test equipment is also a market where the cost of the keypad is a very small portion of the overall chassis cost. Therefore, the keyboard's slightly higher cost is easily justified for better reliability and long service life. Another target market is larger process control equipment. These applications are found in chemical processing plants, large manufacturing plants, and difficult environment applications. Again, the cost of the keypad is very small compared to the cost for the surrounding equipment, and reliability is a must. Let's define a couple of terms. But before proceeding with specific terms and definitions, recognize that we use a group of terms interchangeably, as they are pretty much the same thing. And these are keypads, keyboards, user interface assemblies, tactile dome switch assemblies, and front control panels. Customers can call these collection of keypad assemblies by different names, but we're really talking about the same product. And all of our keypads are custom for each OEM or original equipment manufacturer. Our first definition is a single pole switch. This is the simplest switch in terms of having just two terminals. And when these two terminals are electrically connected, the switch is closed and electricity flows. When the terminals are not electrically connected, the switch is open. Each single switch is also called a pole. So a single pole switch has a pair of terminals that controls one circuit. All tactile metal dome switches manufactured by Suncoast Digital Technology are normally open switches. In other words, the switch terminals are not connected while the switch is, until the switch is pressed, or you press it with your finger. Other commonly found switches, such as toggle switches, have stable states of either on or off, and when you remove your finger, the switch state stays the same. A normally open switch, you remove your finger and the switch opens. Another switch-related term is contact bounce. Simply stated, contact bounce is unwanted switch circuit noise that's caused by the switch mechanism itself. When the switch contacts strike each other, their momentum and elasticity act together to cause the switch contacts to bounce apart one or more times before making steady contact. The result is rapidly pulsed electric current instead of a clean transition from zero to full current. This effect is usually unimportant in power circuits, but causes problems in logic circuits that respond fast enough to misinterpret the on-off pulses as a data stream. For example, a user entering a series of key presses into a keypad, and contact mounts may be misinterpreted as one or more presses for the same switch. Electronic circuits usually incorporate software debounce, but they have limits as well to avoiding problems with long contact bounce. Very long software debounce results in sluggish response from the keypad. High reliability keypads require low and controlled contact bounce times. When more than one dome switch is assembled into a keypad, the resulting combination is called a switch array and is a mechanical or physical layout as seen by the end user. What's not seen by the end user is the method the switches are connected together electrically. Obviously, individual switches are not required to be electrically tied together in any way. However, the number of circuits from the dome switches can become quite large with larger switch arrays. For example, 20 switches that are not connected together require 40 circuits or 2 circuits per switch. There are 2 commonly used electrical switch arrays for keypad assemblies: a common connected array or a row, column, or XY matrix. The first type here is shown and is a common connected switch array, where one of the 2 terminals for each switch is connected together and sometimes referred to as a common. In logic level switches, this common is referred to is connected to either a logic low or a logic high line. For larger number of switches and arrays, the more usual approach is a row column or XY connection scheme. Although this connection scheme looks much more complicated, the connection method for digital electronics is far more efficient as the number of switches required drops rapidly as the number of switches increase. For any one switch that is pressed, there's only one unique combination of row and column circuits that are actually connected. I mentioned logic level switches a moment ago. A logic level switch array or keypad assemblies are resistive only switches, and with open switch voltage of less than 30 volts and closed switch current of less than 20 milliamps. Tactile metal dome switches are not suitable for high voltage, high current, or capacitive or inductive loads. Logic level switches can control power circuits, but they require suitable electronics buffering. In other words, the dome switches interface directly with electronics rather than controlling the power circuits. High reliability, low profile keypad assemblies use tactile metal dome switches, providing momentary, normally open switches in environmentally sealed switch arrays with suitable interface electronic connectors and finished with graphic overlays or silicon rubber boots. Keypads can include interference shielding, displays, discrete LEDs, backlighting, other electronics, and mechanical hardware such as studs. Keypad assemblies are that. They're assemblies rather than just discrete switches. Our core switch technology revolves around the tactile metal switch dome with supporting structure and aesthetic touches designed for long service life while looking like a keypad that belongs in the application. This means that the keypad must blend into the application styling with colors and other aesthetic elements rather than looking like a standard catalog keyboard or a discrete switch that's mounted on the front of an application. Tactile metal domes were developed in the early 1970s for consumer electronics requiring a low-profile, long-life keyboard, including handheld electronic calculators and television on-set remote controls. During the last 40 years, tactile metal dome switches have continued development and reliability. Suncoast Digital Technology views keypad applications with tactile metal domes as a complete design package rather than a collection of discrete components, such as dome switches, connector, resistors, and capacitors. Tactile metal domes are available from several specialized metal stamping suppliers, but not all tactile domes are created equal or work equally well. Worse yet, some unskilled designers commonly misapply tactile dome switches in keypads, thinking that the dome switches are just another component with no interaction to other parts. Consequently, too many suppliers in our industry do not produce high reliability keyboards because they just don't understand the engineering behind them. Virtually all switch domes in use today are stamped from high tensile strength stainless steel alloy for predictable mechanical life. Properly designed keypad applications using tactile metal dome switches have very low closed switch resistance and very high open switch resistance and very low closing and opening switch contact bounce. Dome switches provide tactile snap because the stainless steel has high tensile strength, and the stamped dome shape defines the applied force versus tactile snap or force deflection curve for dome switches. Now let's see what that really means by looking at the graph at the lower left. The vertical axis represents the applied switch force, or the force applied by pressing with a user's finger. The horizontal axis represents the travel or the distance the center of the dome moves as it's being pressed. With increasing force, the switch dome reaches a level called operate force. All of a sudden, the switch jumps away from the user's finger, creating a tactile feel or a tactile snap. The dome switch travels farther with less and less applied force. The center of the dome switch slams into the printed circuit board below and completes the electrical connection. Now look at the red arrow on the graph, and this indicates a negative slope where the travel increases but the force decreases. Notice that when the center portion of the dome reaches the surface below, applying additional force does not provide additional switch travel. This is indicated by the sharp vertical line on the graph. The difference between the operate force and the release force is the tactile feel or snap that the user feels. Now, many people confuse the tactile snap, which you actually feel, with the operate force, thinking they're the same, and they're really not. On the graph, notice that the V-shaped notch at the point where the dome switch meets the printed circuit board actually controls the contact bounce. If the notch has a very sharp notch, the contact bounce will be minimized. However, if this notch looks more like the bottom of a letter U, the contact bounce can be very long. Engineers call this V-shaped notch a stable servo point, where the slight change of applied force will not change the position of the dome or cause any intermittence. This feature is the reason that the switch has snap feel and is different from being just a linear spring. The photograph shows two common types of dome switches where the diameter of the switch and the free height are some of the factors that determine operate force, snap, travel, and operating life. Let's take a look at the factors that harm long-term performance in keyboards. The first one is non-conductive oxides forming on the tactile metal dome switch. Next is non-conductive oxides forming on the printed circuit board pads below the switch. And next is the outside contaminants entering the switch dome cavity. Next is exceeding switch dome voltage and current limits. And finally, dome switches controlling circuits other than purely resistive loads, in other words, no capacitive or inductive loads. Let's examine these factors individually. First is non-conductive oxides forming on the surface of the metal dome. Now, virtually all stainless steel switches, as we mentioned, are stamped from stainless steel alloys. All stainless steel alloys contain a small amount of chromium, and the chromium reacts with the oxygen in the air and forms a thin layer of chromium oxide on the surface of the stainless steel. Now, this chromium oxide is fully transparent, so you can't see it. The oxide layer seals the iron particles in the stainless steel from the oxygen in the air, so there's no formation of iron oxide or rust. The chromium oxide is what makes stainless steel stainless. It's rarely rusted. You just can't see it. The problem with chromium oxide is it's non-conductive. Chromium oxide can be temporarily worn off by dome use, but quickly reforms. And obviously, a non-conductive switch on any switch surface is a big problem. The next item was non-conductive oxides forming on the printed circuit board pads under the dome switch. Now, printed circuit board plating or finishes over copper other than gold will form oxides and will not be as flat as required for the proper operation of the dome switch. Printed circuit board pads under the switches cannot be bare copper or tin plated or solder plated, as all of these finishes oxide. And again, oxides are non-conductive and are a big problem for switches. Outside contaminants entering the switch dome cavity. Any airborne contaminants such as dirt, dust, dissolved contaminants in liquid form must not enter the dome switch cavity. That's the area right around the dome switch, as virtually all of these contaminants are non-conductive. Exceeding dome switch voltage or current limits. Dome switches operate in a circuit with open circuit voltages exceeding 30 volts or closed circuit current exceeding 20 milliamps will cause contact pitting very quickly. And contact pitting increases the contact resistance or intermittent operation and potentially can overheat. Dome switches controlling loads other than resistive loads. In other words, we really don't want to control capacitive or inductive loads directly. Non-resistive switch loads, such as discharging capacitors or switching inductive loads, will cause switch contact pitting faster than exceeding the voltage and current limits. Contact pitting will increase contact resistance and intermittent operation and potentially overheat. Now that we've listed the factors that can harm long-term performance, let's look at the solutions. First is prevention of non-conductive oxides forming on the tactile metal dome switch. The best solution is gold-plated metal dome switches for the prevention of chromium oxide. Now, the problem with standard gold plating processes is hydrogen-based plating chemistry causes hydrogen embrittlement in the stainless steel, and that dramatically reduces the mechanical life of the dome switch. For example, I've seen standard gold-plated stainless steel dome switches with a mechanical life of 2 million cycles before plating reduced to something like 100,000 cycles after gold plating. That's a huge drop in life. Now, our proprietary gold plating process does not use hydrogen-based chemistry, and it prevents chromium oxide on the surface, and it does not affect the mechanical life, so we do not impair the mechanical life whatsoever. Prevention of non-conductive oxides forming on the printed circuit boards. Okay, we have the same problem on the top half of the switches we do under the switch. Gold-plated printed circuit boards are required for the longest performance. Now, another advantage of gold plating the printed circuit board surface is that the surface is very flat, and for tactile metal dome switches, this helps reduce contact bounce. Stopping outside contaminants from entering the dome cavity. Now, printed circuit boards used with metal dome switches must be designed to prevent the printed circuit board vias under or near dome switches from acting as air vents. Printed circuit boards vias are conductive holes through the printed circuit board laminate that connect one layer of copper to another layer of copper. Now, many commercial industrial custom keypad manufacturers purposely put printed circuit board vias under the dome switches to make the construction easier and for maximizing tactile dome switch feel. Now, consider a toy air-filled balloon. When you press on the balloon presses back with increased force. In the same way, air in and around the tactile dome switch, or the dome switch cavity as we call it, will press back just like a toy air-filled balloon if the dome switch is sealed. Sealing the dome switches can reduce the tactile feel. However, venting the switch is a very big problem because it allows outside contaminants for entering the switch cavity and creating non-conductive switch surfaces. Our design and construction techniques at Suncoast Digital Technology prevent the dome switches from breathing external air in and out of the dome cavity by venting the air around within the assembly but not going outside. Now, obviously, dome switch cavities need to be environmentally sealed for the best long-term performance. Staying within the switch voltage and current limits and using only resistive loads. Once the non-conductive oxide formation on the metal dome switches and the printed circuit board is under control, and we've controlled the outside contaminants from getting into the switch dome cavity, What's left is maintaining the surface, contact surface integrity. Now, to prevent contact pitting, logic level circuits, or rather the dome switch has to interface with logic level circuits or high impedance circuits at levels that will not cause dome pitting. And we never directly control resistive or reactive loads such as discharging capacitors or switching inductive loads. I have addressed the biggest concerns for long-term reliability. However, other design and manufacturing characteristics need to be looked at as well. Most high reliability custom keypad assemblies require shielding from internally or externally generated RF energy or electrostatic discharge. Suncoast Digital Technology can incorporate effective shielding into keypad designs. The shield material must be positioned between the user's finger that presses against the switches and all the circuitry below, including the dome switches. For electrostatic discharges, the discharge path follows the path of least resistance from the charge contained on a user's finger to chassis ground. Electrostatic discharges are built up by walking around in an office environment on carpeting or tile floors and then making contact with a keypad that is connected to ground. It's imperative that this discharge path be intercepted prior to entering any of the keyboard's circuitry, including the tactile metal dome switches, which are part of the circuit. Shield selection and termination methods must also consider the RF frequency involved and the level of interference attenuation required. If an application circuitry is extremely sensitive to interference or the application generates a large amount of high-frequency energy internally, the shield materials have to be selected for proper performance. At the same time, the shield material still must be flexible to allow the switch to operate freely while preserving tactile feel. The best tactile feel for unambiguous switch operation for the end user requires that the tactile feel of the switch is not diminished by the keypad's construction methods or materials. Now, what do I mean by unambiguous switch operation? That's a mouthful. When a switch user presses the switch and has a sense that something has happened, the switch operation is unambiguous. On the other hand, if a user presses a switch and is not convinced that something has happened, we call this ambiguous switch operation. Materials between the switch dome circuitry and the user's finger and sealing of the switch dome cavities can all reduce tactile feel. For the keypad designed to work as intended, the overall keypad design and construction must be coordinated with the customer's engineering staff for a successful user interface product. Now, all of these factors must be dealt with as a combination instead of individual parts to preserve the best tactile feel. Now, keep in mind that the keypad is an assembly, not just a collection of loose components. All the parts of the keypad must work together for a successful design. In summary, Suncoast Digital Technology solves keyboard application problems by combining our engineering talent and decades of custom user interface keypad design and manufacturing experience. Satisfied users are our best salespeople. That's the end of the formal presentation. I'm going to turn the presentation back to Ed McMahon now to talk about Epec's products and design centers. In the meantime, I'm going to look over some of the questions that have been posted by our webinar attendees, and I'll be back in a few minutes to answer a few of those questions. If I don't have enough time to answer all the questions submitted, I will answer each question submitted by email.
Great. Thanks, Paul. If you wouldn't mind moving to the next slide for me. As we had talked about, while Paul takes a few minutes to look at the questions, Epec has been in business for over 62 years, and our business is custom electronic manufacturing in terms of all of these products that we discussed. Everything from battery packs to printed circuit boards, cable assemblies, and the user interfaces that Paul really talked about today. And as you can see, while sometimes we may take for granted how simple a user interface is, there's a lot that goes into making sure that it operates correctly and it lasts for a very long time. And part of the way that we add value to our customers is to provide engineering support on all of the additional products here. If we can go to the next slide, please, Paul. We have design centers and technical support, and these people are here for you as our customers to utilize. Design centers for every single one of our products. And our job here is to help with new designs, is to help with improving old design, is to give technical responses, and to be resources for each of our customers no matter what they have a question on. And again, some of our people are world class. I mean, I think that if you take anything away from Paul's presentation today, I think it is that Paul is extremely knowledgeable with significant hands-on experience in his product line. And that's what we have in all of our different products. And they're here to help you make sure that your design meets all of the requirements that you and your customers have, so that we make sure that over the next 20 years your product is still working, you're making very profitable products, and go forward, your products are world-class as well. So having said all that, I'll turn it back over to Paul to answer some of the questions that you guys have asked.
Okay, thanks, Ed. One of the participants in this webinar has submitted a question, and it's a good question. He says, when electronic components are incorporated into a keypad, where are the electronic components mounted? That's a very good question. The keypad's printed circuit board front side is primarily reserved for the dome switches and internal venting layers, as well as some surface-mount LEDs, and perhaps a couple of surface-mounted current limit resistors for the LEDs. There is really no height available for ICs and the larger surface-mounted component parts, or definitely any of the through-hole components on the front side of the board. However, the rear side of the board, or all of that real estate, is available for electronic parts and connectors. So the printed circuit board accommodates a wide variety of these parts, and they go on the back of the parts. So we usually have a lot of room available. Normally, printed circuit boards are designed as small as possible. That's where we get into a lot of the surface mount components. But in our case, the printed circuit board is really sized by the size of the front panel or the keypad. So it's not really very dense, but there's plenty of room available on the back side for a lot of electronics. Okay, another question asks, what are the differences between flexible membrane keypads and your keypads using printed circuit boards? Well, the short answer is reliability, and the long answer is still reliability, but I think it needs a little bit more explanation. Conventional flexible membrane keypads use polyester substrates or sheets, typically 5 mils thick, with screened silver-filled polymer conductors. And these polyester, the polyester material is picked because of the material's memory. And with repeated pressing, it really doesn't cause permanent deformation of polyester. In other words, the switch will return to open when the user's finger is removed. Now, part of the polyester sheet is screen conductors that forms the tail, and that can be terminated with either a crimp connector or a ZIF connector. The screen polymer conductors are very, very thin. They're typically 0.5 mil to 1 mil thick and needs to be flexible so it can bend with the polyester. Taken together, the screen silver polymer conductors and the thin polyester assembly is fairly fragile and prone to stress fractures at the stress points, particularly in the flex tail area and the connector termination area. For difficult environments, including shock, vibration, white temperature excursions, if we replace the polyester sheets with the screen conductors with a printed circuit board, and it could be a very thin printed circuit board, we can use soldered connections and stronger connectors, and we will have a very robust solution that supports long-term reliability. We can use thin printed circuit boards in place of the several layers of the polyester sheets with a membrane keyboard, including all the adhesive layers that go with it. And we'll still be in the same assembly thickness range as conventional flexible membrane keyboards. So that works out very, very well. We have more questions than time permits during this webinar, so I will go ahead and answer all of those lines by email offline. And I'd like to thank you today for joining us for this webinar. In the next 48 hours, this webinar will be posted on the Epec website, and this will be for your reference or for sharing with your colleagues. And thanks again for your time today. I really appreciate it. Goodbye.